In this episode, we're going to focus on a kind of malware evidence that can be surprisingly useful for intelligence work, even when you do not have a perfect picture of behavior in every environment. Malware behavior can change depending on where the program runs and what defenses it encounters, but some characteristics of a malware sample can be observed without watching it execute. Those characteristics are often called static features, and the reason they matter is that they can travel, meaning they remain recognizable across time, across victims, and across variants in a way that helps you connect related activity. Beginners sometimes assume that static features are only for deep reverse engineering, but you can understand the concept at a high level without needing to dissect code. The key is to treat static features as evidence that can support clustering and hypotheses, not as a magical signature that proves attribution. When you extract and interpret static features with discipline, you gain another way to link samples and campaigns while staying honest about uncertainty. By the end, you should know what static features are, why some travel well while others do not, and how to use them to strengthen intelligence without drifting into overconfidence. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good starting point is to define what static features are in a way that is useful for analysis. Static features are observable characteristics of a malware artifact that can be derived from the file itself rather than from its runtime actions. Some static features are structural, like how the file is organized, what kinds of resources it contains, and what metadata it carries. Some are textual, like embedded strings that might include commands, domain names, or user agent patterns, though you must treat these carefully because they can be removed, obfuscated, or planted. Some are cryptographic or fingerprint-like, such as hashes, which uniquely identify a specific file but do not always generalize to related variants. Static features matter because they can be gathered even when you cannot run the malware safely or when you only have the artifact from a collection source. They also matter because adversaries often reuse components, libraries, and build processes, which can create repeatable static patterns. The discipline is to recognize which static features are durable enough to be useful across cases and which are too brittle to support clustering. To understand what it means for a static feature to travel well, it helps to think about how adversaries change malware over time. Attackers can recompile code, change packing methods, modify strings, and adjust configurations, all of which can alter surface-level features. A static feature travels well when it is relatively stable across those changes or when it represents an underlying habit that is costly for an operator to change. For example, a simple hash does not travel well across recompilations because even tiny changes produce a new hash. On the other hand, certain structural patterns, certain repeated resources, or certain consistent build behaviors may persist because they are part of the attacker's tooling pipeline. The point is not to find one feature that never changes, but to identify a set of features that, when combined, makes a relationship more plausible. Beginners often want a single silver bullet, but intelligence work is usually about converging evidence. Static features are one more evidence stream that can converge with behavior and infrastructure links. Hashes are often the first static feature people learn, so it is important to understand their strengths and limitations clearly. A hash can uniquely identify an exact file, which makes it useful for confirming that two parties are talking about the same artifact. That can be valuable for incident coordination, for deconflicting reports, and for ensuring you are not mixing samples accidentally. The limitation is that a hash is extremely brittle as a clustering tool, because small changes produce new hashes, and attackers can easily modify a file to evade simple hash-based matching. Beginners sometimes treat hashes as if they represent a malware family, but a hash usually represents one specific sample. In disciplined intelligence, you use hashes as precise identifiers, not as broad indicators of a campaign. If you want to connect related samples, you need features that generalize beyond exact matches. Understanding this prevents overconfidence and helps you choose the right features for the right purpose. Another category of static features is structural characteristics, which include how the file is organized and what it contains. Structural features can include the types of resources embedded, the presence of certain sections or patterns, and whether the file appears packed or obfuscated. You do not need to know the internal details of file formats to understand the analytic value. Structure can reveal whether a sample is likely designed to hide, whether it includes embedded configuration data, or whether it includes multiple components. Structural patterns can sometimes persist across variants because they reflect build tools or packers that an operator prefers. At the same time, structure can also be influenced by common legitimate software patterns, so you must avoid treating structure as proof of malicious intent. The disciplined approach is to treat structural features as hints about how the malware was built and how it might behave, then use them as part of a cluster hypothesis rather than as a conclusion. When structure aligns with behavior observations and infrastructure links, it can strengthen confidence that samples are related. Embedded strings are another widely discussed static feature, and they can be very informative, but they also require careful interpretation. Strings can reveal hard-coded domains, command names, file paths, error messages, or even the language and terminology used by developers. When strings are present and consistent across samples, they can help connect variants or suggest how the malware is controlled. The problem is that strings are easy to remove or obfuscate, and attackers can also insert misleading strings to create false attribution or to waste analysts' time. Beginners sometimes treat a single string as a revelation, but disciplined analysis treats strings as low to medium strength evidence unless corroborated. A better approach is to look for patterns across multiple strings and multiple samples, such as repeated formatting conventions, repeated command vocabulary, or consistent configuration structure. These patterns can be harder to fake consistently and can reflect developer habits. When you treat strings as part of a broader evidence picture, they become useful without becoming a trap. Configuration artifacts are a special type of static feature that can travel well because they often represent the operational settings an attacker uses across a campaign. Configuration can include addresses, domains, ports, or behavior flags, and while these can change, the structure of the configuration and the way it is embedded can remain consistent. Even if you cannot extract configuration details perfectly, the idea is that configuration patterns can link samples to infrastructure and to each other. This is where static features can connect directly back to pivoting and link analysis, because a static configuration reference might provide a pivot point into infrastructure clusters. The disciplined approach is to validate those pivots and to consider time alignment, because configuration values can be outdated by the time you see them. Beginners sometimes assume configuration equals current truth, but configuration can reflect planned infrastructure that was never used or infrastructure that is already rotated. Still, configuration structure can be a durable fingerprint of a malware builder's habits. When you combine configuration patterns with observed behavior, you get a stronger basis for campaign-level conclusions. Another class of static features that can travel well relates to build and compilation characteristics, which can sometimes hint at a consistent development pipeline. These characteristics might include metadata patterns, consistent build environments, or repeated library usage that shows up across samples. The reason this can travel is that changing a build pipeline often costs time and effort, and many operators reuse tooling for efficiency. Beginners sometimes overinterpret build hints as proof of identity, but build patterns are better treated as clustering support rather than attribution proof. Multiple unrelated actors can use similar tools, and sophisticated actors can intentionally manipulate metadata. Discipline here means you use build characteristics as one more link that can strengthen a cluster when it aligns with other independent evidence streams. If build patterns are the only link, your confidence should stay low. If build patterns align with infrastructure and behavior patterns, the relationship becomes more plausible. This is how static features contribute to a converging evidence approach. A key skill for beginners is learning to prefer feature sets over single features, because single features are often too weak, too common, or too easy to change. A hash is too specific, a single string is too easy to manipulate, and a single structural attribute can be too common. A set of features, however, can be more discriminating because it is harder for unrelated samples to match the same combination by chance. This is similar to how clustering weak signals works. You are looking for convergence across independent hints. For example, A sample might share structural patterns, configuration structure, and a consistent set of embedded resources with another sample, which together makes a relationship more plausible than any one link alone. The discipline mindset also considers independence, asking whether features are truly independent or whether they all derive from a single shared component, like a common packer. If the features are not independent, they may overstate the relationship. Feature set thinking prevents you from being tricked by one impressive-looking artifact and helps you build hypotheses that survive scrutiny. Static feature extraction also has a role in communication because it can help you explain why you believe two samples are related without relying on vague language. Instead of saying they look similar, you can say they share a consistent set of static characteristics that align with an observed operational pattern while still being careful about confidence. This is especially valuable when behavior data is incomplete, such as when you only have an artifact from one environment or only have partial telemetry. Static features can provide continuity across cases, supporting a broader campaign picture. However, disciplined communication includes acknowledging limits, such as the possibility that common tooling could create similar static patterns. This is where confidence calibration matters again, because static features can suggest relationships with medium confidence, but often need corroboration from other evidence to become high confidence. When you communicate static features as part of a converging case, you build trust rather than hype. To close, extracting static malware features that travel well is about identifying characteristics that remain useful beyond a single sample and using them to support clustering, hypothesis testing, and campaign understanding. You treat hashes as precise identifiers rather than broad signals, and you look for more durable indicators in structure, configuration patterns, embedded resources, and build characteristics. You treat strings and metadata with caution, using patterns and combinations rather than single dramatic clues, and you always consider the possibility of manipulation or common tooling. Most importantly, you use sets of features and converging evidence to build defensible relationships rather than relying on any one feature as proof. With these habits, static features become a powerful complement to behavioral analysis and infrastructure pivoting. Next, we'll extend this by learning how to pivot on malware metadata for campaign reach. Because once you can connect samples and features, you can start mapping how far a campaign extends and where it intersects with infrastructure and behavior patterns you already understand.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.